So this is the last coupling we are going to see in this chapter, but this is another type of coupling. So the first three couplings which we have seen were rigid coupling, and this is a flexible coupling. So there are three types of flexible coupling which are generally used. There is bushed pin type flexible coupling, which we are going to study today, and overlap coupling and universal coupling. So in our syllabus only this coupling we are going to study. So we have already discussed that flexible coupling is used to join abutting ends of the shaft when they are not in an exact alignment. Means like they are not in this alignment. So here if we want to join, but they are at some distance or at some angle or anything. So in that case of a direct coupled drive from prime mover to an electric generator, we should have four bearings at comparatively close distance. In such a case and in many others, in direct electric drive from electric motor to a machine tool, a flexible coupling is used so as to permit an axial arrangement of the shaft without undue absorption of the power which the shaft are transmitting. So let me draw the bush pin type coupling. So it will be of more understanding. So suppose this is the shaft. Mhm. So this is a shaft, suppose. This is a key. So this is a key. This is the hub. This is the suppose center line. So suppose this is the brass bush. So this is brass bush. This is cheese head bolt. This is the head of the bolt, and this is the hub, and below it there is a rubber bush, and this is a bushed pin type flexible coupling. So a bushed pin type flexible coupling is a modification of rigid type flange coupling. So the coupling tools are known as pins, and the rubber or leather bushes are used over the pins. And the two halves of the coupling are dissimilar in construction. A clearance of 5 mm is left between the face of the two halves of the coupling. So here, this here Here there is a 5 mm of distance. This distance, clearance is left 5 mm distance between two face halves of the coupling, and there is no rigid connection between them. And the drive takes place through the medium of the compressible rubber or leather bushes. So this rubber or leather bushes, the drive is taking place. So in designing the boost pin type flexible coupling, the proportions of rigid flange couplings are modified, and the main modification is to reduce the bearing pressure on the rubber or leather bushes, and it should not exceed zero point 0.5 mm, zero point 0.5 Newton per mm square. In order to keep the low bearing pressure, the pitch circle diameter and the pin size is increased. So if you want to design, so suppose L is equal to length of bush in the flange. D2 is equal to diameter of the bush. Diameter of bush. PB is equal to bearing pressure. PB is equal to bearing pressure on the brush, on the bush or pin. N is equal to number of pins. N is equal to number of pins. D1, capital D1 is equal to diameter of pitch circle. Diameter of pitch circle of the pins. We know that bearing load acting on each pin, W is equal to PB into D2 into L. So total bearing load on the bush or pins is equal to W into N. So which is equal to W total is equal to PB into D2 L into N. So this is the total bearing load. Now the torque transmitted is equal to load into radius, as we know that. So which will be equal to W into N into D1 by 2. So which will be equal to PB into D2 into L into N into D1 by 2. So the threaded portion of the pin in the right hand flange should be tapping fit in the coupling hole to avoid bending stress. The threaded length of the pin should be small as possible so that direct shear stress can be taken by unthreaded neck. And the direct shear stress due to the pure torsion in the coupling halves, tau, is equal to W divided by pi by 4 d square d1 square. So this force upon unit area, that is shear stress. Since the pin in the rubber or leather bush is not rigidly held in the left hand flange, therefore tangential load W at the enlarged portion will exert a bending action on the pin, and the bush portion of the pin acts as a cantilever beam of length L. Assuming a uniform distribution of the load W along the bush, the maximum moment on the pin M is equal to W into 1 by 2 plus 5 mm. We know that bending stress sigma is equal to M by Z. So M we know W 1 by 2 plus 5 mm divided by section modulus, that is pi by 2 d1 cube. Since the pin is subjected to bending and shear stress, therefore the design must be checked either for maximum principal stress or maximum shear stress by the relation, that is maximum principal stress is equal to 1 by 2 sigma plus under root sigma square plus 4 tau square, and maximum shear stress on the pin is equal to 1 by 2 under root sigma square plus 4 tau square. The value of maximum principal stress varies from 28 to 42 megapascal. So after designing the pins and rubber bush, the hub key and flange may be designed in similar way as discussed for the flange coupling. So let's see another example. For bushed pin type flexible coupling, so it will get more clearer. So here we have to design a bush pin type flexible coupling to connect a pump to a shaft transmitting power P is equal to 32 kilowatt at 960 rpm. So whenever you get power and speed, so with this help we can find torque T. So that is P into 60 divided by 2 pi n, so which should be equal to 3183 Newton meter. Then it is given the overall torque is 20% more than the mean torque. So K T mean T max will be equal to 1.2 into T mean. So T mean we have found, so it will be equal to 382. So it was 318.3. Here it was point, so it would 382 into 10 raised to 3 Newton into mm. We also now, so we have to find this all. So first is shear stress, crushing stress for shaft key material, and vice all we have to find. So now we also know that the maximum torque transmitted, what is the formula T max with respect to shear stress. First we have to find the shear stress. So T max is equal to pi by 16 tau d cube. So pi by 16 tau d cube. So T max we have pi by 16, we have d. D we don't have, but shear stress tau. Tau, do we have tau? Yes, we have tau because it is given. The allowable shear stress is given. So shear stress is given as 40 megapascal and crushing stress is given as 80 megapascal. So tau we have. So with this help we can find D, so which will be equal to 40 mm. So we'll get 36.5 mm, we'll round off, so we'll get 40 mm. So we have discussed in rigid type flange coupling that the number of bolts for 40 mm diameter shafts are 3. So in flexible coupling we shall use the diameter of the pins n is equal to 6. So diameter of pins D1 is equal to 0.5 d upon root n is equal to 8.2 mm. In order to allow for the bending stress induced due to compressibility of the rubber bush, the diameter of the pin D1 may be taken as 20 mm. So length of the pin of the diameter, that is D1 is equal to 20 mm, is threaded and secured in the right hand coupling half by a standard nut washer, and the enlarged portion of the pin which is in left hand coupling half is made of 24 mm diameter. On the enlarged portion, a brass bush of thickness 2 mm is pressed. A brass bush carries a rubber bush. So assume the thickness of rubber bush as 6 mm. Overall diameter of the bush D2 will be equal to 24 plus 2 into 2 plus 2 into 6, which is equal to 40 mm. That is 40 mm. And the diameter of the pitch circle of the pins D1 will be equal to 2D plus D2, so it will be equal to 132 mm. So we know that the bearing load acting on each pin W will be equal to PB into D2 into L, so it will be equal to 32 L. So this will be equal to 32 L Newton. So maximum torque transmitted T is equal to W into N into d1 by 2. So W is in the form of L. So this we will get T we have. So if we substitute this, we will get L is equal to 30.1 mm. So we will take it as 32 mm. So W will be equal to 32 into L, so which will be equal to 1024 Newton. So direct stress due to pure torsion in the coupling halves, tau is equal to W divided by pi by 4 d1 square, which is equal to 3.26 Newton per mm square. W we have, d1 we have, that is 20. Since the pin and the rubber bush are not rigidly held in the left hand flange, therefore the tangential load W as at the enlarged portion will exert bending action on the pin. Assuming a uniform distribution of load W along the bush, the maximum bending moment on the pin M will be equal to W into L by 2 plus phi. So which is equal to 1024 into 32 by 2 plus phi. So section modulus Z is equal to pi by 32 d1 cube. So we know that the bending stress sigma is equal to m by z, so which is equal to pi by 32, sorry, so which will be equal to 27.4 Newton per mm square. So maximum principal stress is equal to 1 by 2 into sigma plus under root sigma square plus 4 tau square, and maximum shear stress is equal to 1 by 2 into sigma square plus 4 tau square into under root. Since the maximum principal stress and shear stress are within limits, therefore the design is safe. So now if we want to design for hub we know that is d is equal to 2d and L is equal to 1.5d is equal to 80 and 60. Now we will check this with the shear stress, so which is equal to T is equal to pi by 16 tau d raised to 4 minus d raised to 4 upon d, so which is equal to 94.26 into 10 raised to 3 tau c, so which is equal to so this will get tau c is equal to 4.05 MPa. So since the induced shear stress for the hub material, that is cast iron, is less than the permissible value 15 megapascal, therefore design is safe. Now we will see design for key. So third, key design. So therefore since the crushing stress for the key material is twice its shear stress, that is sigma c is equal to 2 tau k, we will use square key. So we find that for 40 mm diameter, W is equal to 14 mm and thickness T is equal to W is equal to 14 mm from the design data book. So length of the key L is equal to 1.5 D is equal to 60 mm. So now let's just check this induced stress in the key by considering the shearing and crushing. So for T max is equal to, for shearing, first T L W tau k d by 2. So from this tau we will get as 22.74 MPa, so which is less, and T max for crushing is equal to L T by 2 sigma ck d by 2. So sigma ck will get 45.48 MPa, which is also less. Since the shearing crushing stress in the key are less than the permissible stress, that is 14 80 megapascal respectively, therefore the design for the key is safe. Fourth, for flange, we will design for flange. So for flange, thickness of flange we are taking as 0.5 d, which is equal to 20 mm. So now let's check this stress. Now let's check for the shear stress. So T is equal to pi by d square 2 tau c Tf, so which will be equal to tau c will get as 1.9 MPa. So since the induced shear stress is less than 15 megapascal, so design of flange is safe. So this is the whole equation, whole example. I hope you got. So this is the last lecture of this chapter. Thank you very much.